Hi, and today's lecture is going to be on the second part of FIR filters with respect to how we do the digital filter design. So, in most filter applications, we really care only about the magnitude response, but in some cases, the phase response actually is going to be important. And for particular cases like this, we'll be in like an audio to avoid echoes, and for anything that requires distortionless transmission. Now, if you recall that if we separated a frequency signal, h omega, we would have obtained its magnitude component here, given by the modulus, and its phase component here, given by the angle sign. So, when any signal is passed through a system or filter, for it to remain distortionless or for it to have distortionless transmission, the signal form needs to remain unaffected. And basically, the output signal could be a delayed and scaled replica of the input signal, so long as its general waveform properties and its shape tends to be somewhat similar to it. So there isn't a loss of information in the process, or the signal has not become corrupted. So the system itself needs to make sure that it amplifies or attenuates all the frequency components in that signal uniformly. It needs to be across the entire signal. So the magnitude response in this case needs to be uniform within the signal frequency band. And the same also holds true for the frequency components. They also need to be delayed by the same discrete time value. So this meaning that the number of samples is delayed by, all the frequency components in that signal must be delayed by that same number of samples. So for distorted transmissions, all those properties are violated. So that means all the signal frequency components will also be amplified or attenuated differently, and the frequency components themselves may be delayed differently as well. It's not going to be uniform across the entire signal. So for phase delay, it's basically a relative delay that is imposed on a particular frequency component of the input signal. And its equation here is given in the green highlighted block. The delay factor is basically going to be this part here, where we have the angle of h omega being divided by omega itself, and it's a negative form here. And remember, this part here, what we're calculating for, is measured in samples. So for distortionless response, the phase delay basically needs to be frequency independent, meaning that it needs to be uniform for each frequency. So as such, that equation that we just saw will just resolve into a constant form altogether. So that means in this constant form here, alpha, all the frequency components of the signal for distortionless transmission will be delayed by that alpha amount of samples. And once this property is satisfied, we refer to this filter as a linear phase filter. And we'll see visually why in a few slides as to why the phase of the filter, is linear in nature. So let's examine an arbitrary Z sequence here. This is referred to as a symmetric sequence. Reason for this being is that there's a center point here at Z to the power 0, and then we have an associated Z to the negative 1 and Z to the positive 1, and Z to the negative 2 and Z to the positive 2. So for any symmetric sequence, there will be a center point, and then there will be equivalent positive and negative powers of Z accordingly. Also note that the components here for each one of these positive and negative powers are the same. For Z to the negative 1 and Z to the positive 1, the same component here is going to be B. And for Z to the negative 2 and Z to the positive 2, the same component here is going to be A. So if we try to transform this h of z into h of capital omega, this basically transforms into this part here. And we can see that wherever we had z to the negative 1, it just transfers to e to the minus j omega accordingly. We also could recall that this exponent form here can be represented as a sum of cosine and j sine. In this case, if there's a negative sign, it will be cosine of this component here minus j sine the component. And if we apply that exponent transition, meaning the Euler expansion, to that equation, we can get it in terms of only cosine, because all the sine components in this case for a symmetric sequence will cancel out. And this form here that we observe is referred to as a constant phase relationship. The reason for this being is that any symmetric sequence is going to exhibit constant phase behavior. Now, if we also observe this sequence here for h of z, because there are positive powers of z in this sequence, this is referred to as an anti-causal sequence. If we need to make it causal, on the other hand, we just need to delay the entire thing by z to the minus 2. So a causal sequence will only contain negative powers of z and the z to the 0 power. Once there's a positive power of z, the sequence is going to be anti-causal. This delay factor that we applied here to make the signal from anti-causal to causal is basically just a time delay. And if you can recall from all the previous lectures when we were doing the Z transform in particular, this time delay is basically the amount of samples we delay by accordingly. So the question we're going to ask is, how did we affect the phase behavior of h of z? So if we transform from z into omega, and we see the map property here in the green block, this basically indicates that the time delay just gives us a constant phase delay. And as of such, the overall linear phase behavior is not affected. So a causal symmetric sequence still maintains that linear phase no matter what. So any symmetric sequence that you may encounter will always have a linear phase. And any filter designs based on these sequences will also have a linear phase. So for example, if we had the symmetric sequence here, which is symmetric about this point, and we plot its magnitude and phase response, we can see here that magnitude is represented by the blue line, and it has its own property and so forth. But the important part is that we're watching the phase, which is represented by this red line, and you can see that it has a very linear relationship as it goes throughout the entire frequency band. So for digital filters in particular, the design of it is going to depend on the transfer function. And because we deal with finite impulse response filters, or FIR filters, these are non-recursive designs, so they're just full feed-forward designs. So the question we're going to ask is, how do we design a filter to a specific order regarding for a finite impulse response? So we typically start with the ideal filter response. And this must be symmetric in nature. In particular, when you're doing analog filter design, these tend to have infinite impulse responses, because they're always dealing with continuous time signals, and those time signals don't have an end. Now, there's a different type of filter design known as infinite impulse response, or IIR, that we'll be discussing in the next few lectures. But for this lecture, we're going to be discussing how do we make a finite impulse response, or FIR filter design, so forth. So let's watch the typical low-pass filter and its response. So if we had a fifth-order Butterworth low-pass filter, we can see that this is generally the impulse response for it. And this is actually an infinite response, because it just keeps on going no matter what. But we can also observe for the entire response that it hits some steady state here accordingly. And all the other samples here is just wasted space. So in transforming this infinite response to a finite response, we can just stop after a certain amount of samples. So we could just say stop response after n samples because there's no further change. And in truncating that infinite response, or infinite impulse response, IR, this creates the finite impulse response, or the FIR filter design, which we require. The truncation, on the other hand, will give a variation in the frequency response between the original and the truncated version. This gives us to the first important point when we're doing digital filter designs, that it is an approximation of the continuous filter design or the analog filter design. The equation for the finite series of impulses here is given in this blue block here. And the two things we need to note is that there's no feedback, as you can see. It is only feed-forward parts. And the transfer function is in this form here, in the yellow block. If we do some analysis on this transfer function, we can see that basically this transfer function is going to have all zeros, and once it has all zeros, the transfer function shows that it's going to be absolutely stable. So there's no chance for this impulse response for a finite impulse response filter, or FRL filter, that's going to be unstable. It's always going to be stable. So there are different design methods, which is time sampling or window based, which we just now did, and there's a frequency sampling method. The time sampling method starts with some ideal frequency response for an example, a low pass filter. So we can have basically a rectangular window here, which is basically the frequency response for an ideal low pass filter. Once we have this response, and we have it in terms of h at f, we need to figure out what is going to be it in terms of h of n. So we know that for a rectangular window, when we transform this into h of n, we get our nice sinc curve accordingly. And the equation for the sinc curve works out to be 2 multiplied by the cutoff frequency divided by the sampling frequency of sinc 2 pi n fc on fs. It is important that you memorize this equation because it may come in your exams and it tends to be quite important. Sometimes the equation is not given. So the time response is basically infinite, and then we need to truncate the h of n sequence here symmetrically. So we need to know how many samples do we take in this truncation. And taking the amount of samples, we need to make sure that it's odd because we need to maintain that symmetric property. The truncation here is very similar if we multiply that h of n by a rectangular window w of n of length n, where capital N here is the number of samples. The multiplication here, because it's done in frequency, is also similar to a convolution, and vice versa. So convolution in the time domain is a multiplication in the frequency domain. Convolution in the frequency domain is a multiplication in the time domain. So basically what we just did there is that we put a rectangular function across the frequency response here. We just multiply the two and we obtain our truncation of n samples. Now when doing this truncation, remember this imposes a period of n samples on the signal. And as of such, this imposed period means that the sample frequency response is going to be somewhat different. And this is referred to the spectral leakage, which we did in a few lectures back. To reduce the effect of the leakage, we basically use a sampling window, and we saw that there are different sampling windows that we can do to mitigate the effect of spectral leakage. And these taper the transitions to 0. So those sidebands that we observe, when we have specialized windows, it mitigates the additional frequency effect for those sidebands. Typically, we tend to use the Hammond window. And it's slightly different here from what we observe in lecture 9. As to why it is different, I'm going to leave you guys to conduct a little bit of research to find out why it is this way for the FIR filter design. Let's actually consider a practical example where we're going to actually design a filter. So, we're going to consider a low-pass frequency filter with a cutoff frequency of 5 kHz and a sampling frequency of 20 kHz. And we're going to be using the Hammond window here along with it. So we know FC is going to be 5 kHz and our sampling frequency, referred to as F here, is going to be 20 kHz. We need to figure out what is going to be our H of n first. And we know the H of n equation was given in this form here, which is required to be memorized. Because this is in sync, and some calculators don't have sync, it maps to this form here with respect to sign accordingly. So if we plug in our FC and F, this being F of S here, we can get our H of n equation in this form here. We also need to make sure that the number of samples we take is going to be symmetric. If we wish to figure out how we solve for sync here, in MATLAB, or the mathematical rotation here, sync of t is actually sine of pi t divided by pi of t. So as of such, this means that H of n here could go 0.5 sync of 0.5 n in this form here from MATLAB. We also will be given our window function. So this actually will be given to you, its equation. Once we have our H of n equation here, as we saw on the previous slide, and we have our range of n that we need to solve for, we substitute each value of n here in order to get a value for H of n accordingly. So we'll have for H of minus 4, H of minus 3 go all the way up to H of plus 3 and H of plus 4. This will result into a vector of values. So this will be for minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. And we also do the same thing where we substitute in capital N and common N accordingly. Capital N here is going to be 9 because it's going from minus 4 to positive 4, so that's 9 samples. And common N here indicates the index for which we're going to be solving for. So we also obtain a vector W of n for minus 4, minus 3, minus 2, and so forth. And it's going to be the same length as H of n. We then multiply each one of these values here across for H of n and W of n. So this value here will multiply by this one for the negative 4 index. For the negative 3 indexes, these two will multiply, and so forth as we keep on going. So we'll end up with the H of n by W of n vector values here. And it's going to be symmetric about this point, the 0 index. We can see that basically the symmetry is that we will have the same value for 1 and negative 1. Same thing for 2 and negative 2. 3 and negative 3, and 4 and negative 4 accordingly. Because the n terms here is 0, we can just neglect this for the final answer. And then we can write this out in terms of z, because those indexes were indexes for the z power as well. This form here, however, is causal, because we're going to z to the positive 3. So that means we need to delay the entire sequence by 3 samples. So if we are required to obtain the causal filter design, we need to delay this entire equation here by 3 samples and get it in terms of negative powers of z only. And this will actually be the final answer for FIR filter design. The example with the Hammond window show that for the rectangular window, if we use this, we will get this response here. But for the Hammond window, we get a nice smoother response overall. The ideal response will be in this part here, because we had a cutoff frequency of 5000 Hz or 5 kHz. So this is the magnitude response that we're observing here. The phase response is given by this green line here. So we see that we maintain our linear phase response accordingly by using the Hammond window. The frequency sampling method, which is the other method for FIR filter design, is where we start with a suitable frequency response, and it needs to be from an established design or from an arbitrary response. And this method is really good for unusual filter designs. We then sample the frequency response, and then we find the inverse discrete Fourier transform, which will give us the two-sided sequence. We then find the Z transform, and we right shift to create the causal filter response. For this course, however, we will not be doing the frequency sampling method. We will be only focused on the time sampling method. So recapping what we did in this lecture, we basically saw that for FRI filter design, we need to obtain a symmetric sequence. And that means we start with the ideal low-pass filter response, and then we multiply the ideal low-pass filter response after we know the number of samples and we obtain the vector values by a window function, which is typically given. You are required to remember the equation for the ideal low-pass filter response. Once we obtain the vector values for h of n, being the low-pass filter frequency response, and the window function w of n, we just multiply each of those vectors together. And the multiplication is done by the indexes. So the -4 index will multiply by the corresponding -4 index, and so forth as we keep on going on. Once you obtain the final answer there, if the question asks for the causal filter, we're going to have to delay it to make sure there's no more positive powers value of Z throughout the entire equation. And then that will be the entire final answer. So that brings us to the end of FIR filter design. Our next lecture will be for IIR filter design.